You know that amazing rainbow effect you get when light shines through a piece of glass? Ever wondered exactly how that works? Well, today we're going to break it all down. We are going to follow a single ray of light on its incredible journey to uncover the physics behind that beautiful splash of color. Yeah, it's absolutely gorgeous, right? But the physics behind it? I think that's even cooler. And believe it or not, to understand that entire rainbow, all we really need to do is follow the path of just one single ray of light. So, let's do it. All right, first things first, we're going to trace this ray's journey. And to do that, we need to get our vocabulary straight. We've got a few key angles to define that will map out its entire path from start to finish. Okay, first up, we have the angle of incidence. We're just going to call it I. You see our light right here, labeled PQ? As it comes in from the air and hits the prism, I is the angle it makes with that dotted line. Now, that dotted line is called the normal, and it's just an imaginary line that's perfectly perpendicular, at a 90-degree angle, to the prism's surface. So I is basically our entry angle. Now, the second that light hits the glass, which is way denser than air, bam, it bends. And this first change in direction is what we call the angle of refraction, or R1. It's the new angle that the ray, now traveling along path QR, makes with the normal, but this time it's on the inside of the prism. And let's not forget our main character here, the prism itself. It has a super important feature, the angle of the prism, which we label with a capital A. It's literally just the angle at the very top of the triangle. For any prism you pick up, this angle is fixed. And trust me, it's a huge player in figuring out how much that light is going to bend in the end. So our little light ray has traveled through the glass, and now it's time to leave. It hits that second surface, and whoosh, it's back out into the air. And guess what? It bends again. We call the angle it makes on its way out the angle of emergence, or E. And just like before, we measure it from the normal line. You can see it there with the ray RS, heading off on its new path. Okay, so we've got the whole path mapped out. We know the entry, the inside path, and the exit. But what's the big picture? How much did the light's direction actually change from where it started to where it ended up? That's the real question, right? We need to measure that total bend. Seriously, just picture it for a second. If we took that prism away, the light would have just kept going, straight as an arrow. But the prism got in the way and bent it not once, but twice. So, what's the grand total? How much did it get knocked off its original course? Well, this total bend has a fancy name, of course. It's called the angle of deviation, and we use the Greek letter delta for it. All it is the angle between the straight path the light wanted to take and the final path it ended up taking after going through the prism. It's the perfect way to measure the prism's overall impact. Okay, so we know what it is, but can we actually calculate it without having to draw and measure it every single time? Oh, absolutely. And you're going to love this. The formula for it is actually surprisingly simple and elegant. But before we get to the big formula, we need one little piece of inside information, literally from inside the prism. It's a neat little geometric trick. It turns out that those two internal angles, R1 and R2, will always add up to the prism's top angle, A. Remember that, R1 plus R2 equals A. It's going to be super important in a second. Okay, let's build this thing step by step. The first little bend when the light enters, that's just the difference between the angles, so it's I minus R1. The second bend when it leaves, same idea, it's E minus R2. So the total deviation, our friend delta, is just those two bends added together. So delta is I minus R1 plus E minus R2. Now for the magic trick, we can rearrange that a bit. And remember how R1 plus R2 equals A, we can swap that in and boom, we get this beautiful simple formula. The total deviation, delta, equals I plus E minus A. How cool is that? So that formula is great. It works all the time. But things get really interesting when we start playing around. See, the total amount of bend, delta, isn't constant. It actually changes depending on the exact angle you shoot the light in at, that angle of incidence, I. So let's dig into that and see if we can find something special. Okay, check out this graph. This right here is the key to the whole thing. Along the bottom, you have the angle you're firing the light in at. That's I. And going up the side, you have how much it bends in total. That's delta. So this curve shows us exactly what happens to the bend as we change our aim. Let's trace it. See? If we start with a small angle I and start making it bigger, look what happens to the deviation, delta. It goes down. It gets smaller and smaller, and then it hits this one single bottom point. And if we keep making I bigger past that point, the deviation starts going back up again. It makes this perfect U shape. That sweet spot right at the bottom of the U, that is incredibly important. It's called the angle of minimum deviation, and we call it DM. And here's the kicker. For any given prism, there is only one special angle of incidence that will give you this absolute minimum bend. It's a totally unique situation. So what's the big deal about this one point? Well, it's all about one beautiful word: symmetry. In pretty much every other case, the path of light takes is lopsided, it's asymmetrical. But hit that magic angle of minimum deviation, everything lines up perfectly. The path becomes perfectly symmetrical. The angle it goes in at, I, is exactly the same as the angle it comes out at, E. And on the inside, those two angles, R1 and R2, become exactly equal. It's just perfect. All right, so we found this one unique, perfectly symmetrical case. So what? Why does it matter? Because, my friends, this is the key that unlocks the prism's deepest secret. This is the big payoff we've been working towards. Because everything is so symmetrical here, our math gets way, way easier. Let's take that deviation formula. Delta equals I plus E minus A. Well, at minimum deviation, delta becomes dm. And since I and E are the same, we can just say dm equals 2I minus A. You do a little bit of rearranging, and you get this nice, clean expression for I. And for the inside, remember R1 plus R2 equals A? Since they're both the same now, we just have 2R equals A. Bam, another simple expression, this time for R. Okay, so now we have these super simple ways to find our angles I and R, but only in this one special case. Why go to all this trouble? Because now we can use these to calculate the single most important property of the glass the prism is made of. Its refractive index. And here it is, the moment we've been waiting for, the Prism formula. The refractive index, which we call N21, equals the sine of A plus dm divided by 2. All of that over the sine of A divided by 2. This is huge. This formula lets us figure out a fundamental property of the material itself just by measuring a few angles. Wow, okay, let's take a breath. We just went from following one little ray of light to a formula that tells us about the very nature of glass. Let's recap what we've learned. Think of this as your new physicist's toolkit for prisms. So, here's what you need to remember. First, that simple geometric rule inside the prism. R1 plus R2 always equals A. Then we've got our general formula for the total bend, the angle of deviation. Delta equals I plus E minus A. And the grand finale, the Prism formula, which only works at minimum deviation, lets us find the refractive index. There's even a simplified version for super thin prisms. This is basically the whole story. So we started with a simple prism making a rainbow, and we ended up with a formula that measures a deep, fundamental property of matter itself. Pretty cool, right? So I want to leave you with this one last thought. Now that we have this tool, this ability to precisely measure and predict how any piece of glass will bend light, how does this one piece of physics unlock our power to build everything, from the simple eyeglasses that let us see clearly, all the way up to the gigantic telescopes that let us gaze at the farthest edges of the universe?